Now that we know how to draw Lewis structures and we know how within Lewis structures we need to give every atom an octet, we are going to look at exceptions to that rule, the octet rule. There are three kinds of exceptions. The first one is having less than an octet, which is called an incomplete octet. Then there is an odd number of electrons, which also results in having incomplete octet. And lastly, there is something called expanded octet, where you have more than 8. Let's look at all three. And you will not encounter a lot of Lewis structures with this kind of exceptions, but when you do, it's important that you realize that it's an exception based on the fact that it cannot get an octet, or it needs more than an octet in other cases. So here we have BeH2, beryllium hydride. The total number of electrons, valence electrons in beryllium is 2, 1s2, 2s2. So that 2s2 has 2 electrons. Each hydrogen has 1 valence for a total of 2 because there are 2 hydrogens. So we have 4 valence electrons. Beryllium is in the center. We draw a single bond and we run out of electrons. Hydrogens don't have any. We cannot make a double bond. We cannot do anything. And so this is the Lewis structure. Hydrogen only wants 2, so it is satisfied. That's the octet rule for hydrogen. But beryllium wants 8. It wants to look like neon, but it cannot. It has only 4. So that's your incomplete octet. This molecule does exist even though it does not have an octet. And we are going to have to accept that it exists without going through all those 5-6 guidelines we saw earlier. What about another molecule, nitric oxide, NO? If you count the total valence electrons, nitrogen has 5, oxygen has 6, that's 6 plus 5, 11. You make a single bond between them. There is no such thing as a central atom here because there are only 2 of them. And then you give an octet to 1, and whatever you do, you will be left with one of the atoms with less than an octet. Now here oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It has an octet, while nitrogen has 1, 2, 3, 4, 5, 6, 7. And there is no way to come around this. There is no distribution of electrons or bonding, triple bonding, single bonding or anything that's going to give nitrogen an octet. Please try that. It's a very good exercise. Try to see what other structures you can have. But the reason it cannot have an octet is because there are odd number of valence electrons. And so we are stuck with what we have. We have 11 electrons and all of them are here. Lastly, an expanded octet, which is very common. Expanded octet happens for elements in the third period or below third period, fourth period, fifth period and sixth period. And it may happen when though there are atoms which can have more than 8 valence electrons, such as 10 or 12 or even more. How is that possible? Because they have the 3d orbital. Remember 3d. When you have the second period electrons, you have 1s2 followed by 2s2 and 2p6. So there is only the p orbitals, 3 of them for a total of 6 electrons, and the s orbital for 2 electrons, 2s2 and 2p6. But when you are in the third period, you have the 3s2, 3p6 and 3d10. So because of that d orbital, you can place more electrons in there. Here is an example of phosphorus pentafluoride that has 40 valence electrons with phosphorus in the center, and if you draw the structure correctly, this is what it will look like. The fluorines are from period 2, so they only have 2 valence electrons. But phosphorus is in period 3, so it can accommodate more than 8. The fluorines have only 8, phosphorus has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is this wrong? No, it's not wrong, because phosphorus is in the location on the periodic table where it has the d orbitals available to place more electrons. So these are your 3 exceptions to the octet rule, and in the next video we will look at something known as the Vesper theory, which is what the Lewis structures allow us to predict.